Let's talk about some exciting new developments in CPU and GPU cooling techniques, and TSMC's direct water cooling, and a little bit about what's wrong with that and what we can do better. I'm Oscar from Elmar Technologies, and let's jump right in here. So we can jump over here on the PC that is actually running our cooling system here at the moment. But yeah, this is TSMC's direct water cooling thing. But let's jump backwards here a few steps quickly to explain what all of this hoopla is about. So the GPU or CPU chip, of course, produces a lot of heat, and too much heat for that to like dissipate normally into the ambient air. So you need to distribute that over to a larger area, because if the medium you're cooling to has a very poor heat transfer coefficient, you need a really large surface area to get a small enough temperature delta. So yeah, typically we'll have a air cooler, which, for instance, uses heat pipes here to distribute the heat into a larger surface area. So it heats up this plate here, and that heat gets transferred over into heat pipes that then transfers the heat over to a larger surface area, and then the air being blown here around these cools down that again. Then if you want more power density, you need to go over to another type of air cooler that uses a liquid as the heat transfer medium between this CPU section and the air. Of course, you can run larger radiators and all that stuff also. And yeah, then when you start wanting to run even higher stuff, so then you need to get rid of more of these intermediate steps, because that increases your temperature delta. So that is what TSMC is doing here now. And I think Intel supposedly was doing this also. Okay, but let's look at what happens here. So we have the circuitry underneath here that actually is producing the heat. So let's see what that actually looks like in one of these. So you have, this is like a typical CPU, but this is like just the heat spreader part. This has been delidded. So actually delidded, like we run it without the lid. It's not delidded if you still have the lid on it. Yeah, so let's zoom in here. So this is what that looks like. This is the small one here is the actual calculation die, and this is the I/O die on the Ryzen 3 and 5 platforms. And yeah, so the underside here is what actually produces the heat. Then you have that small chip on here. Then you have some kind of a, so this would be some kind of heat transfer medium, and then this lid here would in the traditional case be these parts. And yeah, then you get the heat transfer from here with some kind of heat transfer media, and then on top of this is what this would typically be. But you need all kinds of temperature delta to get the heat transferred first through this, then through this area, then through this area. So you have lots of millimeters stacking up where you need lots of temperature delta to be able to get that heat out. So of course, if you can bring this cooling medium or the heat transfer medium closer to the heat source, then you can run a much lower temperature delta. So if you're running, like we have now here, ambient 26 degrees air, for instance, and you have a maximum temperature of the circuitry here of 90 degrees, something like that you want to run that at, then yeah, you have a certain temperature delta that you can manage to use. And yeah, this is what TSMC and Intel are working on now, is to fit this sort of heat transfer area here directly down on the circuit piece here, so you get rid of all of these intermediate parts. But there is a problem with this, and that's why you see these large sort of dips here. So this is what you would typically see on current state-of-the-art sort of liquid coolers that are actually just liquid heat transfer units to ambient air. But they have these dips here. This is to increase the surface area to the water, because water again is a very poor has a very poor heat transfer coefficient. So you need to have a large surface area to be able to transfer heat with a small temperature delta into the coolant. And yeah, that's why you have these sort of slits here to increase the. Let's actually zoom in on this a little bit. So that is why we have these, to increase the surface area. And yeah, that is basically because of this phenomenon. Also partly, so you have a flow here really close to the surface, basically 0. And then when you have a boundary layer that is also has very poor heat transfer, then you end up needing lots of surface area instead to compensate. But there is a downside here is, yeah, you're producing heat here and you want to remove that over to a coolant. So ideally you would want to do that here because, yeah, if you have this part sticking up here is almost the same height as this area. So you're basically transferring the heat on average to like halfway up these slots here. This increases the temperature delta that you need to run on average to get the heat out into the coolant. And yeah, we have a solution for that we do a correct sort of way to do direct water cooling. And that is to just run that cooling on these units directly. So if I can, I'm going to have to show it over on this camera because I can't get that to focus otherwise. So as you can see on this, we have I/O die section there and 2 CCDs. This is for a Ryzen 5 type platform. So we have this is the first unit. So we have a cooling entry. Now let's actually see if I can maybe do that here. Oh, it actually kind of works. Okay. Yeah. So we have a coolant entry here for a CCD. This is for a 2 CCD, but this CCD just hasn't been drilled. So we have a coolant entry for 1 CCD here. The coolant flows around and then flows over the I/O die on the way out, basically to cool the I/O die also. And yeah, this was the first version we ran. Then we have a slightly newer one. So yeah, we have a lot of these different versions of these. This is just some to show. Come on, can we get this to focus? I think we can. Come on, there we go. Yeah, so we've got lazy and just deleted this second CCD here to speed up cooling and try sort of all kinds of different ways on how to optimize this and reduce the boundary layer as much as possible. And yeah, as you can see here, we have this is like a small amount of all of the different ones we've tested. We do machine these in-house, so that's really the only way to do this. As you can see, I mean, this is just that goes directly on that, and we have a separate one for the GPU system also. And yeah, the sort of performance we can get from that is kind of decent. Let's just zoom this in a little bit. So this is actually from this very chip here. Just to jump over to the screen. So this is from this very chip, a 3800 XT. So this is with stock behavior, and yeah, then with aftermarket leading custom loop sort of manufacturer. I mean, it's pretty much all the same. It doesn't really matter much because it all comes down to, wait, how can I show this? Yeah, because it all comes down to like they have the same fin thing, and it doesn't really matter what manufacturer you're using. But yeah, with that we were able to run it up to what was this, 4.7, this looks about 4.575 gigahertz, and yeah, we were able to run that at 100 megahertz more with our direct cooling system. And yeah, I tested this at 20 degrees Celsius also, and we're able to bump that up slightly more with 9 degrees more temperature delta. So quite decent. Let's just show you guys graphics benchmark stuff also. Yeah, so this is the cooling block we have on the GPU here currently, and some quick results from that. Just zoom that in also. It of course depends on what kind of a power density you're running and how that works really, like how beneficial this is. I mean, the higher power density you want to run, the more beneficial it is to reduce this height as much as possible. So basically what we could do is, instead of running these fins, we could just run a flat surface, which we currently are running. And yeah, as you can see on this chip here, this is absolutely flat. There's no trickery, no no grooves or anything like that. And this was something that we've been running now for a year on the test system here. And yeah, so far no problems cooling wise, longevity wise, anything like that at all. So definitely possible without any kind of fancy grooves or anything. This is like technologies that's available today that is, yeah, better than these sort of research technologies that TSMC and Intel are working on at the moment. So yeah. But I mean, I guess they'll catch up to us eventually. We were planning on patenting this, but seeing like actual papers on this sort of direct water cooling. This is completely different, of course, because the technology we're using is to be able to run a flat surface, which reduces the height needed even further, which allows a much more effective cooling. But being able to enforce a patent based on techniques to like reduce the this boundary layer effect while still maintaining like reasonable pressures and fluid flow stuff and things like this, that's not really going to work against like giant companies like Intel and TSMC. So yeah, we're just putting this out into the public domain, basically this technique. Of course, we're not going to show you guys our latest developments and stuff like that. I mean, if someone at TSMC, Intel, IBM, whoever like makes yeah, these mainstream sort of calculation supercomputers, stuff like this. I mean, this has a huge benefit also from a power perspective, because you can reduce the cooling requirements a lot, or otherwise with the same cooling power, you can reduce the temperatures of the actual chips running, and that reduces their power consumption, so you can get some significant gains with that. But yeah, we're not going to show you guys the latest techniques that we are running on that. Yeah, because of that. I mean, we're happy to sell all the data and technology we have on that to give some companies some head start, or we could potentially do some samples for CPU overclocking guys, whoever. I mean, running a sort of direct liquid. So that would actually be direct liquid cooling. Some overclocker or something were to run like a liquid nitrogen or something through this, which would hugely benefit. Because what they typically would do is first have the heating section here at the bottom, then would be running the actual silicon chip, then the transfer to the actual lid, and then on top of the lid you would have like a liquid nitrogen container, so you end up having a huge temperature delta over this whole package. And that's of course not very ideal. You like have this like top surface with the liquid nitrogen extremely cold, but then this actual chip component here is actually running like very reasonably high temperatures because of the large temperature delta you have to run. So yeah, this could be interesting for like fun sort of overclocking stuff and things like that also. But anyway, that's it for today. And hopefully see you guys on some of our other crazy projects. Bye.